Identifying pancreatic cancer is difficult since it is hard to detect the disease early on. By using a Kegel dataset, this project looks into the classifications of urinary biomarkers for pancreatic cancer detection. There are three algorithms for classifying the data that we use in this project, which are 1R, knife-based, and classification regression trees, CART model. Pre-processing the data, choosing features, and evaluating the model using the accuracy was part of this project. The outcome demonstrates how successfully each algorithm separates pancreatic cancer patients from healthy individuals. Pancreatic ductal adenocarcinoma (PDAC) is one of the deadliest cancers, with only 9% of patients surviving for more than 5 years. Urine proteomic biomarkers such as creatinine, LYVE1, REG1B, and TFF1 offers a promising non-invasive and inexpensive diagnostic method for PDAC. The first objective of this project is to obtain and ensure data quality for analysis by pre-processing a Kegel datasets of urine biomarkers associated with pancreatic cancer. To employ and educate 1R, knife-based, and CART algorithm for the purpose of categorizing pancreatic cancer according to urine biomarkers. And the last one is to analyze model performance by comparing the model efficiency in detecting pancreatic cancer using metrics such as accuracy and ROC-AUC. The first methodology is business understanding. The aim of this project is to create a classification model using urinary biomarkers in order to address the problem of pancreatic cancer diagnosis. The second methodology is data understanding. Exploratory data analysis (EDA) was conducted using a Kegel dataset that has 14 attributes, including sample ID, patient cohort, sample origin, age, sex, and others. It is to discover potential challenges and opportunities. This involves understanding data distributions, identifying missing values, and investigating features relationship. Then the third methodology is data preparation. It is to make sure the data set is ready for modeling. We clean and transform it. This covers handling missing values and normalizing numerical attributes. The fourth methodology is to cover data modeling. Predictive models are constructed by applying three classifications algorithm: 1R, knife-based, and CART algorithm. Cross-validations and performance metrics including accuracy and used to train and evaluate in each model. Choosing the most relevant features and improving the models are all part of this iterative process. And the last methodology is model evaluation. An essential part of the development process is model evaluation. It evaluates the model's quality, and compatibility with the requirements. This stage identifies areas that want to improve and involve diagnostic procedure to make sure the model operates as planned. Statistical significant evaluations also guarantees correct data management and interpretations.
Okay, next is the dataset analysis and visualization. Okay, we have a total of 14 variables in our data set, which first is the sample ID. It's a unique string identifying each subject. After that, we have the patient cohort. Cohort 1 represents the previously used sample, while cohort 2 represents the newly added sample. And next, we have the sample origin. BPTB, where it represents the Bart Pancreatic Tissue Bank at London, UK. LIV, which represents the Liverpool University at United Kingdom. And UCL, where University College London at United Kingdom. And we also have age, where it represents age in years. And sex, where M represents the male and F represents the female. After that, we have the diagnosis. Okay. In diagnosis, 1 represents the control variable, where is no pancreatic disease, and 2 is the burning hepatobiliary disease, 119, of which the patient have chronic pancreatitis, and 3 is the pancreatic ductal endocarcinoma, where the patient have pancreatic cancer. After that, we have the stage. Okay, for stage, we represent with 1A, 1B, 2A, 3B, and stage 3 and stage 4. And next, we have the burning sample diagnosis. For those with burning, non-cancerous diagnosis, what was the diagnosis? Okay. For those with diagnosis, they have a non-cancerous pancreatic disease. And next is the plasma CA199. Okay, in this, the blood plasma levels of the CA199 monoclonal antibody that is often elevated in patients with pancreatic cancer is recorded. After that, we have the creatine. Creatine acts as a urinary biomarker of kidney function. And next, we have the LYB-E1. This represents the urinary levels of lymphatic basal endothelial hyaluronal receptor 1, a protein that may play a role in a tumor metastasis. This is very important to detect whether a patient has a pancreatic cancer or not. Next, we have the RAG1B. This is to detect the urinary levels of a protein that may be associated with pancreas regeneration. And next, we have the TFF1. This is to detect the urinary levels of trefoil factor 1, which may related to regeneration and repair of urinary tract. And last but not least, we have the RAG1A, which is to detect the urinary levels of a protein that may associate with the pancreas regeneration. And as we can see, this is we can see the overview of the data set at here. This is the example. Next, we have the analysis and description of the data set. The data set has over 590 rows and 14 columns in total. The dataset covers a diverse mix of data types, including both numerical, which are continuous and discrete, and also categorical variables. And next, we have also the data types are also integers, floats, text, and also categorical variables expressed as numbers. We can see the summary of the data at here. Okay. Next, we also have the issues in the data set. Okay. The data has 524 rows with missing values. It significantly reduces the sample size, potentially bias the sample if the missingness is not random, and diminishes the statistical power of any analysis or modeling efforts. As we can see in the data, as we can see at stage and burning sample diagnosis, there are many values that is null. Okay. In descriptive analysis, we replace the missing values which are null with a descriptive value such as null. As you can see now, we have replaced the stage variables and burning sample diagnosis where the variable sum of the data are null to none because this is a descriptive value.
Assalamualaikum, my name is Shakira. I will now move on to the data modeling section. So for data modeling, we use three models which are 1R, naive Bayes, and CART. First, I will explain 1R model. 1R model presented for classification is designed to map different stages of an attribute to specific diagnostic categories. For this model, the classification rules are straightforward. All stages are uniformly classified as diagnosis 3, while instances with no stage are classified as diagnosis 2. This approach is simplistic but allows the assessment of the model's performance based on a clearly defined set of rules. Next, we have the naive Bayes model. Naive Bayes predicts the target variable diagnosis using all other dataset features. Laplace smoothing, applied with a parameter of 1, addresses zero probabilities that might occur if certain feature values are absent in the training data. The prior probabilities indicate a notable class imbalance. As you can see, class 3 is the most prevalent class. This imbalance suggests that the model may frequently predict class 3, potentially skewing performance and leading to biased predictions favoring the majority class. Finally, there is the CART model. The CART model classifies the dataset into three classes by using a series of splits to maximize accuracy. Initially, with a complexity parameter or CP of 0.63, the root node shows a high error rate of 1. As the CP decreases, the model's complexity and accuracy begin to improve. After the CP is reduced to 0.01, the error rate also drops to 0, with a cross-validated error of 0.151, indicating effective pattern capture. The key variables in the model are benign sample diagnosis and stage, with importance scores of 26 and 24 respectively. Plasma CA99 and age have moderate importance, while LIVE1, REC1B, sample origin, and TFF1 are less influential. The decision tree structure highlights how different nodes lead to specific classification outcomes.
The provided images depict key urinary biomarker data for pancreatic cancer classification. The first image is a histogram of the age distribution in the sample with a higher frequency of individuals aged 60 to 70 years, peaking around 70. The second image is a plot of REG1B versus LYVE1 levels, colored by diagnosis categories, indicating that diagnosis 3 clusters at higher LYVE1 values, whereas diagnosis 1 and 2 are more dispersed. The third image is a box plot showing creatinine levels by sex, revealing that males have slightly higher median levels and more high-value outliers compared to females. This visualization collectively highlight the differences in biomarker levels, age distribution, and their interrelationships, which are crucial for data analysis in pancreatic cancer classification. For the discussion, firstly is 1R. The Pearson's chi-squared test indicates a statistically significant divergence between the observed and expected frequencies in the contingency table. This highlights a fundamental limitation in the model's ability to accurately reflect the complexity of the data. Next is naive-Bayes. The model demonstrates notable strengths, particularly in its accurate classification of class 3 with all instances correctly identified. Inherent class imbalance poses a challenge against balanced and fair predictions. Next is CART model. The CART model accurately classifies observations. The complexity parameter CP table reveals how the tree evolves through pruning, balancing model complexity and predictive accuracy. For the conclusion, the development and evaluation of classification models for urinary biomarker-based pancreatic cancer detection in this data science project provided significant novel insights as well as challenges. 3 classification algorithms, CART, 1R, and naive-Bayes, were applied, and the results included a variety of performance indicators and insights. These results highlight the need for advanced data handling methods and ongoing model monitoring to improve pancreatic cancer diagnosis precision, and patient outcomes. That's all for me. Thank you.